Okay, let's start the implementation now. In order to do the implementation, we will first need an example puzzle. So in that case, let's construct an example puzzle in the tenth folder. Let's create a simple text file in another editor. Let's say we will just then copy and paste that into our folder. So we'll just add the puzzle we have. So we have tents. Actually, we have trees. So we have 0 for empty place and T for trees. So let's create the original puzzle. So we have 0, 0, 0, 0, T, 0, 0, T, 0, 0, T, 0, 0, 0, 0, 0. And let's do it puzzle 1. And let's also create another very, very simple puzzle, which is something like this. Okay, so let's do it puzzle 0, actually. Okay, let's copy and paste the puzzles to our folder so that we can actually utilize those puzzles in our project. Okay, the puzzle 0 is very easy puzzle. So in that case, we have a tree here, a tree here in the corners. So we can place the tents either here or there. And then if we place a tent here, we cannot place a tent here because then there will be diagonal. So we can place a tent here. If we place a tent here, then this next solution will be here. It's like that. So for the puzzle 1, that's actually the solution for next to the question in the original puzzle. Okay, so then that's actually the thing we done. So let's then construct our methods. So the first method which will be available is actually the state reading, the puzzle reading. So in order to read a puzzle, we need a scanner class. So let's have an input, new scanner, and system.in. Actually, not system.in, actually new file, file name. So in that case, we also need to have a try and catch. So let's put it down and we can actually have an input clause. So then we will read the state from the file. So string, let's say line, and we will read line by line, and then initialize, then get the trees one by one from what we have read. Okay, so while actually input has next. So then line equals input dot next, let's say. And then we need to, let's say, find the trees in the in the line. And we also need a coordinate. We need to settle the coordinates. So for that reason, let's say we initialize each time an I. When we read I, then in that case, it is it. So then let's write a function, find or get trees. So the get trees will have the line and I as an input. So in order, since we don't know what will be in the 10th, so we can actually modify the 10th as an array list. So let's do it as an array list. We can easily modify it to a linked list. So let's also modify the trees as an array list. So let's then construct our trees equals new array list. And we will actually call the getTrees method. So the getTrees method will get the trees in a single line. So let's write the getTrees method. GetTrees and x, actually, the x coordinate actually of the tree or row or column. Let's do it not x and y. Let's modify it row and column. So this row will be row and y will be column. So let's modify also this to column. Get row, get column and column. So in that case, x will be actually the row number. So let's put it as row. So this will be the line to be read. And then this will be actually the row. Okay, so we will just search for line for existence of trees. So in that case, we need to go for each character in the line, which starts from 0 to line length. And then if the line character at I equals a tree, which is, for example, here this one or that one, etc. For this puzzle, we see. And then in that case, we will actually add a new tree for that column and row. So in that case, let's see, trees add actually new coordinate row and as a column I. So we'll add new trees for each line to be read. And then that's actually done for state reading. And we also need to know, so in each case, so since we know the size of the trees, so in that case, we don't need actually the tree count. So let's forget about that. And in that case, we can easily say trees size. Okay, we actually removed the trees. And similarly, actually, we don't need a tenth count because the tenths we have added will be given in the tenth. So we can say tenths dot size. So then in that case, we actually simplified the trees and tenths. Okay. So then let's continue with the construct candidates. So given a state and we have actually, let's say, a set of trees, how will we place a new tense? So we need to have, again, an array, not actually an array of states. We can, again, create an array list of states. So then in that case, let's construct the array list of state as candidates. So which will be new array list, something like that. And we will return actually the candidates. Okay, so how will we construct the candidates? So given the current, let's say, tree. So let's say we have this tree, let's say. where can we place the new, let's say, the new tent? So a tent can be either put horizontally or vertically. So in horizontally, we can place, for example, here, but we cannot place here. So in that case, we have two options for horizontal and two options for the vertical. So at most, we can have four candidates. But we also need to know actually the size of the puzzle so that we do not get outside the boundaries. So in that case, we need also the size of the puzzle. How can we do that? One possible alternative is actually to have actually to read from the file, because we also know the row count and actually column count. So this should be available somewhere else. So in that case, let's put it in the state, row count and column count. So in that case, what can we do is, since we are putting this in row count and column count, we can actually then in that case, we can put this as here, row count, which actually increments the row count each time. And then we can actually have the column count as the length of a line. So in that case, we can do, for example, here, column count equals line dot length. So we can put it here, or we can also put here. So as the last line, because each line we have the same length. So in that case, we can do something like this. So we say line that might not be initialized. So let's put it here. So line will be something like here. Okay, we have the row count and we have the column count. So in that case, since we know the row count and the column count, we can easily now construct the candidates. So how can we construct the candidates? For each actually tree, we can place either horizontally into possible places or vertically into possible places. So then let's construct them one by one. So let's go one by one. But before doing that, we need to have actually a copy of current state so that we can add a new, let's say, tent or etc. So in that case, we can write a clone function. So state clone. And then this clone function will return us a clone of the state so that we can actually do not create new, do not modify the original state. So the clone function will have the same row count and column count. And then it will have the same trees and tents. So let's say, actually, we will not do this. We will write something like state equals new state, where we need actually a new dummy constructor. So let's say public state integer row count integer column count, and then which actually initializes the row count to that row count and column count to that column count. And then we will actually trees equal new array list and tents equal new array list. So this will be an empty state with number of rows and number of columns. And also we should put a tense here so that we don't miss the initialization of the tense. Okay, so for the clone, we will create the same state with number of rows, row count, and number of columns, column count. And then we will give the trees the same. So in that case, we can say copy all trees to the new trees. So in that case, state dot trees add all actually current trees actually, and also state dot tenths add all the tenths, and then we return the state. So we create a clone of a state so that it will be a new state, a possible state. And then we check if the new candidate will have a new tenth at the new position. So let's then get to that. So we can put either horizontally or vertically. So in that case, let's put in a horizontal manner first. So we need to check if we have actually, if we can place a tree in that position. And in order to do that, we have two options. So how can we put a tree? How can we know that we can put a tree here or not? So since we already know the position of the tree here, we need to place one to the left or one to the right, which means we will reduce the column one or increase the column one. And in that case, let's see if the actually, and we need to do this for the current tree. So we need to find the new state as an update to the current tree. So we are concentrating on the current tree. Okay, so construct candidates. So in that case, let's do something like this. So let's find the state first. No, tree first. Actually, not a tree. Coordinate as a tree. Tree equals trees dot get tens dot size. Okay. So if we have 0 tens, then we will get the 0th tree to place. If we have 1 10, then we will get the first tree as the index. So that will be the coordinate of the tree. And then with that tree, we can place either to the left or to the right. So then we will check if the tree get column is larger than 0. That will be the first candidate. Or if the tree get column is smaller than column count -1, because if the number of columns are 3, we can at most place at 2, which means since we are going to the left, so it should be at most 1. So 1, column count 3, it is possible. So then trees get column. And the last one, 3 get row should be larger than 0, the third alternative. And the fourth alternative, if the 3 get row less than row count -1. So all 4 candidates. So we go to left by reducing the 3 columns -1. So we can say, okay, coordinate, let's say, let's declare it here, coordinate 10th candidate. Okay, so then 10th candidate will be new coordinate. What? The number of row is actually current trees row, and the column will be 3 column -1. So this will be the 10th candidate. For this one, the column should be increased by 1. This one, the row should be reduced by 1. And for this one, the 1 will increase the row by 1. So in that case, these are possible candidates. And we check if that 10th candidate satisfies the conditions. So what are the conditions? The conditions are we can not place a tent on top of a tent. So we check for the current tents if we have an exact match for the tents. And also we cannot place on top of the trees. So in that case, let's write functions to check that. So write a function, public Boolean is tent there, any tent there. So we give a coordinate tent candidate, and we checks current tents for the tent candidate. So let's write also an comparable or equals method. So public Boolean equals coordinate. So if the row equals coordinate get row, and column equals okay, so the row should be equal coordinate get row, and column should equal coordinate get column. So return that. And then we can say for any tents in the so okay, for coordinate tent, or let's say current tents, if current equals tent candidate, return true, return false. And we can actually do the same thing as for both trees and tents. So in that case, we can say something like array list of coordinate, some things, let's say, and then we can write actually things. Okay, so if there is any tent there or if there is a tree there, we cannot place. So then in that case, we will write. So if any tent there with tents and tent candidate, if there is no tent and not any trees there, then let's put the quotes there so we can actually shorten it. So if there is no tent there and no trees, no tree there, then there is only another check. Any tent should not be diagonally or any kind of adjacent to that tent. So then we need also check for the adjacency. So public boolean adjacent, any adjacent tent there. So in this case, we write tent candidate and we write this tent and adjacent. And then we can write an adjacent method here. Coordinate adjacent. And this adjacent will check if there is an adjacent tent there. So given two coordinates, how will we check for adjacent? The rows should be the same. If row equals actually coordinate, not adjacent. If the row equals coordinate get row, and if they are in the same row, but they are difference in columns. So column minus coordinate get column, and the absolute value is 1. In that case, they are adjacent. If the columns are the same, and the rows have one difference, then in that case, they are adjacent. And how will they be diagonal? Actually, the difference in rows multiplied with difference in columns should be actually -1 or 1. So if then so their absolute differences of rows and columns multiplication, if it is 1, then we return true. Otherwise, we return Okay, so we continue with the adjacent. So if any adjacent tent there, so we say if not any adjacent tent there, tent candidate. So we can also do the same for the other one. So in that case, let's write a private function, boolean check tent candidate, which will be at the coordinate candidate, and then we'll write something like this. Tent candidate. If not anything there, so in that case, let's put it in the candidates check add tent candidates. So candidates add tent candidate. It should not add candidates add tent candidate. So in that case, we create candidate this.clone and candidate tent add tent candidate and candidates add candidate. Okay. So in that case, let's put it something like this. Check and add new candidate. So candidates. Okay, check and add candidate. Candidates. New coordinate. So each time we are checking if the candidate satisfies the conditions, and then we, if it satisfies the conditions, we add the new candidate to there. So there are 4 alternatives, and then we do that. Check and add candidate, candidates, new coordinate, and that's all. Okay, we return the candidates. So let's check any adjacent candidate there. We can do it private. Any tent there, we can do it private. So all of them are possible candidates, and we have get trees, and we check if the column is correct. We remove one column, we add column, etc. And then we check and candidate, any tent there, any tent there, anything there. Let's refactor, rename anything there. Say any adjacent tent there. If there are no adjacent tents or no trees or no tents there, then that's a possible candidate to be placed. And then that's actually all. Okay. So we construct the candidates. So state is done. Then coordinate is also done. So we have actually the puzzle. So for puzzle, we will actually create the initial state. So new state with file name. So, and we also need to write the solve, which actually we will get from the book. So let's write it from the book. So we will have actually the new element. So let's say element E equals new element with the initial state. And then we have a Q with a default size. Let's give it 10,000 for now. And then we add the new element. So let's rename it element. Okay. Then while Q is not empty, then we actually get the element by dequeuing it. Actually, we can have the state current state. So element get data. And then if current state is a solution, we just return the current state. If it is not, then in that case, we get an array list of state as candidates, which are actually current state, construct candidates. And then for every state child state, let's say, in candidates, we enqueue that as a new element. So, and then we have element, new element, child state, and then we add this to the queue and queue the element. And that's all. We actually return null here. So that's all. We enqueue the initial state. And then while the queue is not empty, we dequeue the first element and we get the data. If it is a solution, we return it. Otherwise, we construct new candidates. And for each element, we enqueue that, the child state, and then we return null. So that's actually the puzzle. So we have the coordinate finished. We have the element already there, the queue already there, the state already there. Can we do it better? Possibly, let's say. So we also need to check, for example, can we place a tree? No, we don't need to check. And then we have the main. So let's create a puzzle. Puzzle equals new puzzle. Let's say puzzle 0.txt. And then we have state solution will be puzzle solve. And then we should display actually the solution. So in that case, we can print the tents. So let's do a toString. And then sout, not sout actually. So for coordinate tent in tents. So sout tent get row and tent get column. Or we can also write to string method to actually turn row plus empty plus column. So then in that case, tend to string. Okay, actually string result equals this. Result plus equal tend to string plus /n. Return result. So then in that case, S out solution to string. Okay, let's try to debug. So do we have the puzzle? The initial state. We have two trees in 0 and 10. And then let's solve. The solution is 0, 1, and 2, 1. So 0, 1, 2, 1. 0, 1, 2, 1. So what will be the solution? 0, 1, and 2, 1. So that's a correct solution. So let's do the thing and run it. And it's solved. So how many tens we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 0, 2, 0, 4, 2, 2, 1, 7, 1, 0. These are possible solutions. Okay. So in that case, that's all done. So maybe we can add a printing. So we can do something like this. In order to print the result, we can actually print something like this. So instead of this, maybe we can not write the coordinate, but let's get over that. And let's void print. So then in that case, in the main, we can write solution print. Okay. So in that case, we will do something like this. Integer I equals 0, I less than row count, I plus plus, or integer j equals 0, j less than column count, j plus plus. So we'll say something like this. If there is a tree there, print the tree. If there is a tent there, print tent. If there is nothing, print 0. So it will be something like this. If we will say anything there, we will, if there is a tree there for this coordinate, then system out print actually a tree. Otherwise, if there is a tent there, then print an X. Otherwise, print a 0. And after every row, print something. Okay, then let's write run the program. So you see there is a tenth. So this is a solution. So this tree is there, this tree is there. This tenth is for that, this tenth is for that, this tenth is for that. 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 And this tenth is for that. So that's the correct solution. And no x is to Noah. So let's see also puzzle 0, which is correct. Okay, so that's the end. Let's go over. So we have the state, and in each state we have trees, tents, and then we have actually constructed the construct candidates, and we add 4 possible candidates. We check, and then for everything we have any adjacent anything there and any adjacent there, and that's all.